2871.7 and tolerable touch potential and tolerable test potential. Although it is tolerable 2.40.5, but we put 2 to 4.1, much lesser than this, and step potential we put much lesser than this. Although it is tolerable 761, we put 337. And the ETAP software gives us an idea that how much will be the total artment design, what will be the length, what will be the breadth in x direction and y direction, and what is the gap of the grid. So that's why we design our artment. Now I'll come to the power transformer protection. We will do the little bit of this thing. We usually see the work current protection and arc fault protection issue. In a work current relay, there would be essential and current coil. Normal current flows to this coil, and the magnetic effect generated by this coil is not sufficient to move the moving element of this relay, as it is the condition of the restraining force is greater than the reflecting force. That means when the overcurrent is flowing to a particular line, the CT feeds the secondary current to the relay, but the relay's restraining force is much greater than the deflecting force. When the magnetizing force is much higher than the restraining force of the relay operates. So when currents will be greater, the magnetizing force will be greater. So restraining force, it beats the restraining force, the current relay will be operated. So that's how the entire operation is being explained over here, and that is the circuit diagram. You see the transformer over here is the load. Now there is a CT, secondary is short circuited. At the same point, there are two overcurrent relay and one number ground fault relay. When in any CT, the current flows through it greater than the I think the main current set for the variations, the relay operates, and then VCB operates, and the circuit opens. Now this is the two number phase fault overcurrent relays and one number ground fault relays in providing overcurrent protection, the star delta transformer that is being given over here. This is the arc fault current, the same situation, but arc fault relative. So when any arc fault occurs, the current flows through it. The secondary winding of the current actuates the relay, and relay actuates the strip circuit, and strip circuit activates. Now this is the situation, the overcurrent and arc fault. That is the scheme we usually see, the two overcurrent and one arc fault over it. Now there are CTs, it is short circuited and arc. Now you see the two overcurrent relay and one arc fault relay. It is this analogy is same for the 11 kV feeder also and 30 kV feeder also. Now suppose there is a overcurrent through this R phase, so the CT feeds the extra current over here, and at the Kirchhoff law said that there is a point, the current should be divided, the summation of the current through in any point should be 0. So if the extra current flows to this point, so this point, the extra current would be again going back to the same point through R phase and Y phase. So there will be no current flowing to the R phase. So there will be activating overcurrent relay. But if there is any arc fault, suppose there is an arc fault over here. So this point and this point is this point of the R phase, and this point is the same point. So current flowing through this, and this comes to the arc fault relay and goes to this point. So overcurrent and arc fault both activate. So in this way, the entire zone will be operating. This is the differential protection scheme. This is absolutely for basically for 10 MVA transformers. This is the differential protection. This is the primary phase, this is the secondary circuit. When the current flows to the primary circuit, the CT flows the I1, and current flows the secondary circuit, the current flows to the CT is I2, and it's going through the I think differential relay, and it nullifies each other. So differential relay is set in such a way that when it falls occurs, then only the difference in such a way the differential relay will activate, otherwise it will not. So when everything is normal, the little bit of difference of current is there due to the ratio, but that does not actuate the differential fault. But any fault happens in between the transformers, the differential relay actuates not only transformer. Differential protection zone is from 33 kV CT to 11 kV switch gear. So huge zone covers. So in that case, the difference between the two currents happens, and the differential relay actuates, and it activated, and the circuit goes off. This is the basic diagram of differential protection. See, this is a start side. To compensate that, the CT is being connected as a delta side. This is a delta. Sorry, this is a start side. This is a delta side. So CT is being connected as a start side to, I think, nullify the phase shift. Now this differential protection is activated in such a way, in actual manner. Now this is the through the pilot, or how this differential protection is operating through a strip coil. That so this particular diagram shows that idea. I don't want to elaborate because time is running away. This is the constructions of differential protection. The operations is being given over here. These are differential protections of little bit of limitation. Magnetism characteristics of CTUs, ratio has changed the respect of circulating current. That's a major thing. Pilot work is very, if you very long, the resistance will be much higher. In that case, it cannot actuate in proper scheme, as per the proper scheme. Heavy short circuit current may cause the saturation of flux of the CT. That may give the abnormal result or abnormal operation of the differential protection. Tap changing may lead to the setting and improper operations, and inrush magnetizing current, that is also creates the improper operation. These 4 or 5 limitations we usually take care in case of that differential protection scheme. That is restricted arc fault. In differential protection, the current will be huge, but it is certain fault happens, very small leakage current that takes place. In that particular case, we usually took care all these things. It takes care through the restricted arc fault relay. So it is being over here. That is a neutral current and neutral CT, and this is RYB. So the same way it is functioning. The neutral CT, when it is everything is perfect, this current and this neutral CT current will be almost same. So this is not actually activates. But if certain internal leakage current flows, so that comes usually through the NCT, and the difference of the current takes place, and restricted arc fault relay operates. And it is very close zone. It is not the broad zone or as much as like differential protection relay, but it is a very close zone. Internal transformer, if something happens in the transformer internally, it takes care of the that thing, that restricted arc fault protection relay. That is being given over here. Now protection of incipient faults, that also done by our restricted protection. Now it is Bush's relay. It is a gas actuated relay, because I don't want much more. I just want to give you some idea about the diagram, then it will be understandable to everybody. So this is the main tank. Usually Bush's placed in between the conservator and the transformer main tank. This relay placed over here. Now when something happens internally, and gas is going to be evolved from that particular heat generation point or fault point, so gas usually goes up, and it creates such a environment that is oil goes down. When his oil goes down, this float will be coming horizontal, and this NONC contact will be coming, the alarm circuit, and announcing the circuit gets actuated, and the alarm goes on. Again, the gas is going evaporating, gas is cropping up. So the oil level of this conservator continuously going down. When it goes down to that level, then the tip circuit actuates, and the Bush's relay actually sends a signal to the auxiliary relay, and auxiliary relay sends a signal to the master trip relay of the transformer control point, and this master trip relay has every control to activate the VCB, and the circuit breaker goes off. That is the major thing of Bush's relay operations, and that is being given over here. This is the Bush's. Operating time is 0.1 second to 0.2 second. No, I just don't want to elaborate. This is overcurrent protection, strip 85 to 90. Same thing is the alarm, and if you see the oil temperature and warning temperature, they have got the same thing like which was the alarm signal as well as the trip signal. So alarm signal is comes to 80 degree and trip comes to 85 to 90 degree. Basically, it's the same thing from oil temperature and warning temperature indicator through the master box. Through that wire it goes to the auxiliary relay, and through auxiliary relay it goes to the master trip relay. Initially, for alarm, auxiliary actuates the alarm circuit, and for trip, auxiliary actuates the master trip relay, and master trip relay actuates the VCB, and the VCB goes off. This is the actual circuit given over here. How this differential protection CT is being placed and restricted output CT is being placed. That is being given over here. And now this is a little bit picture. We have seen the winding temperature, oil temperature, pressure relief valve, how it is being done, and pressure release operation. If pressure arises inside the transformer exceeds a preset pressure limit, then the safety valve opens it up with tap which held by a spring and releases the internal pressure. That is done automatically, but transformer doesn't trip. SCADA. Then I will talk a little bit about SCADA. Then I finish it down. Usually supervision, control, and data acquisition. Usually we introduced in so many systems. We introduced in Siliguri, introduced in Kolkata, introduced in different substations in Salt Lake. We introduced in Asansol also. And basically, you see, we have got the SCADA center in Kolkata, maybe, or Asansol, whatever. So, from substation through RTU or MFF, we get the data, and this data through MPLS link goes to the SCADA server of Asansol SCADA center. And there is a central SCADA center of Asansol Kolkata SCADA center. It is called DR. So DC, data center. So this SCADA data obviously simultaneously go to the data center at Calcutta, and is backup is being restored in Behrampur DR center, data restoration program. What we do, we practically collect all the substation data. See, there is a supervision, control, we can control it sitting in Asansol data center or sitting in my office. Through that software, I can switch it on or switch off of any 11 kV switch gear, 33 kV VCB. We can